Have you ever stopped to think about the quiet, humming magic that keeps our world, well, cool? We are surrounded by these incredible feats of engineering that we totally take for granted, from the fridge in your kitchen to the massive systems that power our supermarkets. Today, we're going to pull back the curtain on one of them. I mean, really think about it. You walk into a grocery store, you've got freezers keeping ice cream rock solid at way below zero, right next to coolers keeping drinks perfectly crisp, and then open displays for vegetables that just need a gentle chill. How on earth do they manage all that? Your first thought might be, well, they must have a huge room in the back filled with dozens of different machines, right? One for each temperature. But that would be incredibly complicated and, frankly, a total energy nightmare. And luckily, that is not how it works at all.
The real answer is so much more elegant. It relies on a single, super smart system that can juggle all those different cooling jobs at once.
But before we can get into the genius of how it multitasks, we need to look at the 4 basic tools that make any kind of refrigeration possible. Let's build our foundation here. First up, we've got the compressor. You can absolutely think of this as the heart of the system. It's the workhorse. It sucks in a low-pressure refrigerant gas and just squeezes it, which cranks up its pressure and its temperature. This is what drives the whole process. Okay, so next, that super hot high-pressure gas flows into the condenser. And its job is pretty simple. Get rid of heat. It works just like the radiator in your car. As that refrigerant sheds its heat, it literally condenses from a gas back into a high-pressure liquid. Now, for a little bit of physics magic, this high-pressure liquid hits something called the expansion valve. Think of it like a tiny, precise gatekeeper. It forces the liquid through a small opening and bam, the pressure just plummets. And that sudden drop in pressure makes the refrigerant instantly become incredibly cold. And that brings us to the final piece, the evaporator. This is the part that's actually inside the freezer or the cooler. The super cold refrigerant flows through these coils, it soaks up heat from everything around it, and in the process, cools that space down. As it absorbs all that heat, it boils back into a gas, and it's ready to head back to the compressor to start the whole cycle over again. Okay, so we've got our 4 basic tools, right? The compressor, condenser, expansion valve, and evaporator. Now, how do we use them to solve our supermarket problem? This is where the engineering gets really, really clever. And here it is. This is the breakthrough. Instead of needing one of everything for each cold space, you use a single, powerful compressor and condenser that serves multiple evaporators. The trick is how you split the flow. Let's trace the path here. That one big compressor and condenser do their jobs for the whole system. But then, after the condenser, the liquid refrigerant, see this, it splits into 3 separate lines. Each of those lines gets its own expansion valve and its own evaporator. So you've got one for the ice cream, one for the drinks, one for the produce. Then, after they've done their cooling job, the now gaseous refrigerant from all 3 evaporators merges back together before heading back to the start. So the whole secret, the crucial point, is this. You get different temperatures not with different machines, but by precisely controlling how much refrigerant flows to each individual evaporator. It is one system with multiple, independently controlled cooling zones. Just brilliant. But you know engineers, right? They're never satisfied. That first design is great, but what if you need even more control? What if you need more precision? Well, that leads to even smarter system designs. For instance, what if your cooling needs are worlds apart? Like you need a deep freezer holding meat at, say, -18 Celsius, and right next to it, a crisper for vegetables that needs to be a cool and humid 2 Celsius. Those are completely different environments. And this is where the design evolves. On the left, you see our original system with one big compressor for everything. But for next-level control, you move to the system on the right, a multi-compressor system. Here, each evaporator can get its very own dedicated compressor. This gives you incredibly precise, independent control over each zone. So what's the trade-off? Well, it's pretty clear. The single compressor setup is simpler and cheaper to build. It's fantastic when your target temperatures are all pretty close to each other. The multi-compressor system, on the other hand, it's more complex, it's more expensive, but it gives you that pinpoint temperature control that is absolutely essential when you have really different cooling needs. All right, so you might be thinking, this is getting really complicated. Multiple valves, multiple compressors. It might seem like overkill, but there is a very, very good reason for all of it. And it all comes down to one word: efficiency. At the end of the day, the goal here isn't just to make things cold. It's to get the absolute most cooling power you can out of every single watt of electricity you put in. For a business like a supermarket or an industrial plant, energy costs are a huge deal.
And engineers have a specific way to measure this. It's called the coefficient of performance, or COP. You can just think of it as a simple efficiency score. It's the amount of cooling you get out divided by the energy you had to put in to get it.
You know, a really great way to think about this is like miles per gallon for a car. A higher COP number means your system is way more efficient. You're getting more cooling miles, so to speak, for every gallon of electricity. It's the gold standard for performance.
So, what does a good number look like in the real world? Well, in one of the engineering examples from our source material, a complex industrial plant that was using 2 compressors achieved a COP of 2.67.
And what does that number actually mean? It means for every single unit of energy that the compressors used, the system moved 2.67 units of heat out of the cold spaces. So you're getting more cooling effect out than the energy you're putting in to do the work. That is efficiency in action. It's incredible.
And that's why all this matters. This isn't just about some clever diagrams on a whiteboard. This is about designing systems that are so efficient they save enormous amounts of energy and money, which has a real-world impact on everything from the price of food to our planet's resources. From the food we eat to the medicines we rely on, these invisible systems are working around us all the time. The engineering today is already so impressive, but as our world gets warmer and our need for cooling just keeps growing, the next breakthrough in efficiency isn't just a matter of saving money anymore. It's a necessity. The only question is, what's it going to be?